Perfect. Hello, good morning. Hope you are doing very well. You had a very nice lecture in the morning by Frank, and are ready for a second lecture before lunch. So, just a recap. Can you hear me well, by the way, or not? Yeah? Okay. So, just to start a recap of what we covered yesterday, I introduced you to alkaline atoms. These are atoms with two outer electrons. We discussed why this unique atomic structure makes them ideal for clocks. We reviewed the properties of Ramsey spectroscopy, how clocks operate, and we were coming to a conclusion that because clocks with neutral atoms operate with many atoms, then we need to understand collisions. We introduced a little bit of the idea of S-wave and P-wave scattering lengths, and now we are going to start discussing another very important property of the collisions of alkaline atoms, that there is the SUN symmetry. So before ending the class, I gave you an example of SU2 symmetry, for example, column interactions, and we introduced the idea that, well, even the interactions are 1/r that is independent of the nuclear spin or the spin of the particles. We introduced the idea, and let me start writing that, so that the idea that, for example, the S-wave interactions, I mean, if I have a wave function that is as in the singlet state, because this force the spatial wave functions to be symmetric of the position of the two particles, then that means that when I write that, for example, interactions of the system, the Hamiltonian can be rewritten in and well, we have this, and we have also the triplet states, for example, up, and the triplet will require the function to be antisymmetric. And for example, for the case of contact interaction, for example, these type of interactions for the S-wave, that only the singlets can interact, we rewrite it as something like is minus S1 dot S2 minus 1/4. So if we put, so here, remember, S dot S is S1x, S1 and 2x, plus sy1, s2y, plus s1c, s2c. And for these can also be rewritten in terms of flip-flop operators with which the corresponding factors s plus s minus, for example, that's complex conjugated. This term is proportional. Let's put it proportional, this term here, and this is a CSC. It's clear that, for example, if I have this up state, this term is 0 here, so it's only 1/4. So any triplet, for any triplet, this is giving me a 0 for S-wave interaction, and then the only that one can interact is the triplet. The triplet, when you put this wave function here, it gives you minus 3/4. So this is give you -1. So this is the interaction via S-wave interaction. Yes. So what I wanted to introduce is the idea that this Hamiltonian is SU2 symmetric, since this Hamiltonian commute with the collective operators for two particles, that is going to be the Pauli operator of one plus the Pauli operator of the other particle divided by 2, and same for Sy and 6 for Sc. Yes? And then Sc, the same thing. Yeah. So basically, we concluded that this Hamiltonian is SU2 symmetric, and so the spins only are switched depending of the interaction, depending of the quantum statistics. Yes. So I think that's something that I mean, we are now well known with the helium atom, and I mean, these are familiar concept. Now, however, we are going to extend for the case of SUN interactions, when for example, in strontium, instead of 2 levels, we have 10 different nuclear spins. Yes, because I is equal to 9/2. So in principle, I can have a component that Mi that goes from -9/2 up to 9/2. So there are 10 components. So the idea here is, again, because these atoms have J equal to 0, and I'm going to go back and establish what is actually the validity of approximation, because I also told you that is not completely exact, at least for the triple zero. That's why we can excite the clock. But for the moment, imagine that really, this is the case, that we have a completely j equal to 0 atoms. In this case, I dot j, there is no hyperfine coupling, I dot j is equal to 0, and therefore the electrons, that are the ones that determine the collisional properties, are the only ones that participate, and therefore we have the characteristic again that in this case the nuclear spins do not participate in the collision except via the Fermi statistics. So this gave rise, like in the case of SU2, now we have SUn when n is equal to I plus 1. For example, it's going to be 10 for strontium. And the remarkable consequence is a simplification that in that case, because the nuclear spins do not participate in the collisions, we have nuclear spin independent scattering lengths or scattering parameters. That's a very important simplification. And the other simplification is that I have not spin changing collisions. So let me just introduce a little bit the idea of SUN to make you a little bit more familiar with that first. And second, I'm going to introduce emphasize what is the difference between this type of atoms and the case, for example, of alkali atoms. So for SU2, we are very familiar with the idea of Pauli matrix. Yes, SU2 is the group is associated with rotations. And we know that the group SU2 have 3 generators. That is Sx, Sy, Sc, and of course is the identity, but the identity is trivial. Yes? And for example, these operators can be written in terms of raising and lowering operators that are, for example, this for this, and well, the complex conjugate for this. These are, we are talking about here SU2. Now, in the case when we have n spin levels, well, we can define a similar type of operator that is like raising and lowering operator, but in this bigger space. So in the case of SUN, we can define the fundamental representation of this for an atom I, for example. This is a key. This can be defined as the operator that destroy in M and create in N for a spin I. Yes. So you destroy an atom in this, like very similar here, that you destroy an atom in down and flip the spin up. Here you go from M to N. And the properties, I mean, with these generators, what we can write is that the Hamiltonian for alkaline air atoms, the collisional parts, can always be rewritten as sum over I, S, N, well, with some coupling constants here via J, for example, S, N, M, I, S, N, N, J. Like, for example, for the SU2, I was writing S dot S2. So one of the characteristics of this, so these are the generators of SUN rotations. And the number of generators that are independent is n squared minus 1. So if you go back to the Pauli matrix, in this case, n is equal to 2, and you can see that is 3, that is consistent with this number. So, and the important part is that, again, like what I did for the case of SU2, if I define this Nm, that is sum over I, Sni, that is the collective operator acting, that is sum over the spin of all the atoms before I define it the sum over Sx plus Xx1, Xs2. So what happens is that if you look at this, the Hamiltonian, if you try to compute the commutator between this and this, you find that is 0. So all the Hamiltonian commutes with all the possible n squared minus 1 generators of SUN. That's when we have, in that case, I can say that I have SUN symmetry in the collisions. And this is the case when we are going to write some of the Hamiltonians and of the SUN for alkaline atoms, and you can see that all satisfy this property. So just a hint, or if you wanted to compute this, how is that? And maybe I give you an exercise for doing that. That show that if you have a Hamiltonian in this form, you have this satisfied. For that, maybe an interesting inequality that you want to know is that what is the commutator between SMN and SNQ. So this is going to be, we can derive this. So you have, in this case, you have MN, yes, and then for the first term, you are going to have this SNM, SPQ minus SPQ, SMN, yes. So you are going to have this, and in this case, you are going to have, this is this term, and then I'm going to write the analog of this term. I have P, and you can clearly see that from this, the first term, this is a delta function, yes? So this is going to be a delta function between M and P, and now this is again my raising operator Qn. This is for the first term. Now the second term, that is going to be greeting something like this. Then I will have a minus sign here. So I'm going to have a minus sign. And then I'm going to have the delta function between Q and M, between these two. And then I'm going to have we are going to have this Q and M, and then we are going to have this NP. Yes, so these are kind of the commutation relations that you satisfy for SUN algebra, and with that you can show that this Hamiltonian commute. This is just a little bit of mathematics, but you can show that this is the case. Yes. Okay, so now physics. What I wanted to show you is that when we write Pauli SUN generators, we are going to expand a little bit of a bigger group than SU2 generators, but the role is very similar to Pauli matrix. Just you are rotating in a bigger space, not in a not just in the case of SO3 rotation. It's going to be a little bit bigger Hilbert space. So okay, so this is kind of a little bit of the mathematics, but let's go to the physics. The physics is that there is a nuclear spin independent scattering parameters, and therefore that's going to be one of the key properties, and we are going to count how many scattering parameters I'm going to need. That's one of the part. And the second is that there is no spin changing collisions. That means these Hamiltonians are going to create, so the characteristic here, sorry, I'm going to erase one more time. So the characteristic here is that, imagine that I have my 10 nuclear spin states. And then I prepare, for example, an initial sample that only have these two flavors. I only have 9½ and 7½. The idea is that when I have the atoms, these states are populated, then as a function of the collisions, I'm never going to populate any of these states. So that means that if I start, for example, with only 2, that is SU2, even though I have all the possible accessible levels, I will never populate them. So that simplifies a lot of the physics. This was shown, for example, by Florian Schreck in an experiment when he was trying to prepare. He is trying to prepare different type or start with different type of internal levels, and then he was showing that he was never finding other level in his sample. So basically, he prepared a gas, for example, with only 2 levels with optical pumping, and then he was able by the time of flight measurements and something, an analog of an optical Gerlach experiment, he was able to actually determine how is the spin population of the sample and demonstrate that in this case, this property was always satisfied. Mhm. There are going to be more experiments that I'm going to discuss where we are going to take advantage of that. If people have worked here with alkali atoms, they might be realized or be aware that this is not the case, for example, in rubidium atoms. In rubidium atoms, you have J dot I, of course, different from 0, and the good quantum number is not J or I, well, a moderate magnetic field, but the good quantum number is F, that is the sum of J plus I, yes? So, but that means, and how this manifests in the collisions, is that in rubidium, for example, that you have F equal to 1, that you have 3 levels, -1, 0, and 1, you can have spin-changing collisions. That means if you have one particle with m equal to 1 that collides with a particle with m equal to -1, then you can go and scatter to 2 particles with m equal to 0 and m equal to 0. And these spin-changing collisions have been used in many, many experiments for example, try to generate some type of spin squeezing and in Marcos over Thaler group. And I mean, they have very different experiments that use this as an advantage, as a property, as a plus. We don't have that. It's a simplification of the problem. So this is, for example, for rubidium, is allowed. For strontium, this would never be possible because of the SUN symmetry. And in rubidium, if you remember yourself, for example, you have 2 different scattering lengths. For example, you can have, because if you have one F equal to 1 atom colliding with one F equal to 1 atom, you can have 2, 1, or 0. And because of quantum statistics, actually only the 2 and the 0 collisions are the ones that are allowed. And then you find, for example, for rubidium, you can have a scattering length that is for F equal to 2 something, and for F equal to 0 something. That is different. In the case of strontium atoms, we have a single scattering length that describes the collision properties of the particles. Is that clear?
Just a question of curiosity. You could also imagine having non-spin conserving collision with dipolar.
Yes, yes.
So this is small in rubidium, but still present.
Yes. What happens in strontium? Yes.
So in strontium, you should also have it, right?
In strontium, we could have it, but remember that the dipole moment, I mean, we have a clock state. One is 3, the states that I'm always considering is 1 is 0 and 3 is 0. This is an excellent question. But remember, this is a spin forbidden transition. It's a spin and dipole forbidden transition. So the dipole matrix element between these two is below millidivide, is very tiny. And because the dipole moment between these two is really, really, really tiny. This is different, for example, for the case of rubidium, where the transition with the standard transition, when you can have an spin, dipole allow transition that are much bigger because the line width is of the order, for example, of megahertz. Here we have a line width that there is the order of megahertz. So the dipole moment is 10 to the minus, I think it's 10 to the minus 6 device. It's really, really tiny. So the corrections from collisions, from dipole-dipole interactions are of the order of 10 to the minus 20th or 19. And actually, June is trying to build now an experiment, try to measure them, but they are really, really tiny.
So it's even less than in rubidium.
Much less, because it's a forbidden transition, because of the dipole moment is really tiny, because of the millihertz line width. So, but this is an excellent question, and really one of the current experiments in June that his clock has increased the sensitivity now to 10 to the minus 20th. He's trying to measure this type of dipole-dipole interactions. And then, of course, these are going to flip the nuclear spins. And you can see that in principle, if you can always try to have a decay, for example, just an spontaneous emission decay from 9.5 to 7.5, that this is possible, but it's so long, it happens after 118 seconds, for example. That is not measurement, well, it's very hard to measure at the moment unless you have many, many particles. And you can increase them in some degree. But just standard collisions, just if we are talking about pure collisions, like coming from the C6 coefficient, then these are really, really not allowed. So going back to this question of how much they are allowed and how much they are not, because I told you before that The reason if this transition in strontium 87, this transition is a millihertz bandwidth, but it's allowed, yes? So if this allowed, then I'm violating some of the fact that, the J dot I is not completely zero in these levels, because the 3p0 has a superposition of 3p1, 3p2, 1p1, and remember that's what we discussed last lecture, that the 3p0 has a little bit of mixture of these levels. So now if we try to estimate what is the level of non-SUN symmetry that I have in a collision. So if I'm going to have the difference in the scattering lengths, for example, between the number of nuclear spin components, now I have remember we were drawing yesterday the collisional potential, where this is going to be the short range, the chemical reacting, maybe the short range part of the potential. And this was the van der Waals interactions, like something like this, that we were discussing last time. So if we're going to try to estimate how much you break, if there is any dependence on the scattering lengths from collisions, the simple estimate of this is going to be associated with the corrections of the potential that couple different nuclear spins. The time when you have a collision is going to be determined by the time that the particles collide in this very short range region of the potential. So this is going to be this delta V is the part of the potential that changes, that is nuclear spins. And times delta T, and delta T is the time, this is delta V, and delta T is going to be associated with the time that particles spend in the short time region of the potential. So Paul Julien helped us to compute this time, the time that the particles remain in the collisions. And this time, it depends, of course, on the width and the depth of the short range potential. But for most of the time, for most of the particles of the atoms that we are dealing with, and for most of the temperatures that we are dealing with, that is below microkelvin temperatures, this time is the order of picoseconds. And now let's try to estimate this delta V. For strontium, for the 1s0, the only type, if you look at 3p0, this have F equal to 9/2, yes? This 3p0 have also F equal to 9/2. The first state that is trying to have an F that is not 1/2 is this, that is F equal to 9/2, 11/2, and 7/2. This is the 3p1. This is the one that have different nuclear F. And this is the part that is going to be able to change the nuclear spin, yes, because you can go from 9/2 to F equal to 9/2 to 7/2 or 11/2. So it happens then, but look, this state is very far away in energy from the 1s0. It's very far away. So in order to estimate how much, we are going to use second order perturbation theory, yes? Second order perturbation is the hyperfine. So for delta V, for the 1s0, this delta, I can compute delta V like second order perturbation theories, that is going to be the hyperfine correction to the energy divided by the energy splitting between 1s0 and 3p0, or a 3p1. So divided by delta E. For the type of hyperfine interactions, this is of the order of 300 megahertz. You can look at this number in some a table of the structure of the atoms. You can look at NIS and try to look at what is the hyperfine splitting this, and it's going to be of the order 300 megahertz. And then delta E is an optical transition that is of the order of 400 terahertz. And if you compute this number, then you're going to have something that is of the order of 200 hertz. And therefore, when we are going to multiply for S wave, if we multiply these two, so for S wave interactions, this delta S for 1S0, therefore delta AS divided by SS is going to be of the order of 10 to the minus 9. Very tiny, very, very small, the correction from the violation of SUN symmetry. For 3p0, all 3p0 collisions, or collisions between 3p0 and 1s0, then the delta t is going to be the same, is of the order of picoseconds. But I told you that this state already have some admixtures because it has some components of hyperfine interactions already, yes? That's what we discussed last time. So we cannot use second order perturbation theory, but a naive estimate is just first order perturbation theory, and therefore the mixing is proportional to the hyperfine directly there. So in this case, delta AS divided by SS is going to be proportional to the hyperfine, times delta T. The hyperfine is the order of 300 megahertz. So then you get a number of the order of 10 to the minus 3, much larger than 6 order of magnitude larger than the violation of the SUN symmetry in 1S0, but still very small. And we have not able to measure that deviation for the moment. So this is just a bare estimate of how this symmetry is violated. But with that, I hope that I convince you that this symmetry is, even though not completely exact, is very well satisfied for the case of alkaline atoms. So and with that, we are going to use this assumption to try to understand a little bit more the collisional properties of strontium. Is that clear for everybody?
I just want to, maybe I didn't finish. For which state was the standard power of -3?
-3 for this collision with, collisions between 3p0, 3p0, and 1s0, 1s0. I mean, there are 3 kinds of collisions. I can collide within this. I mean, this is 1s0, 1s0. Collisions, or collisions between atoms in this, or the other is collisions that involve the excited state. So one bad part is that, unfortunately, collisions between 3p0, 3p0 are lossy. So when we have this type of collisions, they are so energetic that we lose the atoms after some time. That's the only going to be bad, disappointing part of that collisions that we are not happy with. But I can tell you how we solve the problem. Is that clear?
Just to make sure I understand. The scatter length is still different in 1s0, in 3p0, and in 3p0.
Yes, right? yes, exactly. That's the next step. I'm going to derive what is the basic ingredients that I need to have to characterize the collisions. Okay, so let's do that and try to see what are the collisions that I need for characterizing. So as I mentioned before, we are dealing with fermions, and for the case of identical fermions, I have p-wave interactions, but I can also have, for non-identical fermions, non-S-wave interactions. So let me start with the case when I have symmetric nuclear spins. So for example, I have 2 states. I can have a collision between atoms in 2 identical nuclear spins. For instance, it can be, for example, 9/2, 9/2. I don't care because the SUN interactions are independent of the nuclear spins. The only thing that I care is that this is symmetric. So it can be MM, or it can be MN plus NM divided by 2. Any type of these kind of effective triplets is what I care. So if I have 2 atoms in a symmetric nuclear spin wave function, then I have 2 possibilities. So this is the nuclear spin. And now I'm going to have the possibility to have symmetric and antisymmetric orbital degrees of freedom. For this, for now on, I'm going to call the 1s0 the G and the 3p0 the E. So there are three possibilities. I can have two atoms in E. I can have atoms in G. And I can have atoms in EG plus GE. Now, my nuclear spin is symmetric. My orbital degrees of freedom are symmetric. So because of Pauli statistics, the spatial degrees of freedom must be antisymmetric. And if the spatial wave function is antisymmetric, the only way that I can collide is via p-wave interactions. Yes? So with that, therefore, the type of collisions in this case are p-wave collisions, and I characterize by a scattering volume BEE. In this case, I have, and all can be different. In BEE, I can have BGG, and in this case, I have what we call BEG, and because it's plus here, I'm going to put it BEG plus. Now I have another choice. I have the possibility to have antisymmetric orbital degree of freedom. In this case, the wave function, the spatial wave function, needs to be symmetric. So these collisions are going to be, there could be a possibility to have collisions that are S-wave. So I'm going to call it this minus. So this is characterized by BEE cube, BGG cube, BEG plus cube, and this is just characterized by a scattering length that I call EG minus. So these are four different parameters that I can have. All right, this is the case where the nuclear spins are symmetric, but I can also have nuclear spins that are antisymmetric. So I can have Mn minus Nm divided by the square root of 2. And then I go to this case. I mean, this is antisymmetric. The orbital degree of freedom is symmetric. That means that I can have S-wave collisions because the wave function can be symmetric because the antisymmetrization is taking care of this. So in this case, I'm going to have UEE, and these collisions are going to be characterized by the scattering length EE. Similar here, I'm going to have S-wave, and therefore I'm going to characterize by GG. In this case, can be again S-wave, and I'm going to have a scattering length that is G plus. And now in this case, I have two antisymmetric contributions. My wave function needs to be antisymmetric, so I need to have collide via p-wave interactions, and I have a p-wave scattering length. So if you count, instead of having n squared minus 1 parameters times 2, I only have 8 different scattering lengths that I need, or volumes that I need to determine in order to characterize the collisions of alkaline atoms. Yes? And yes, so these are again summarized in this table here. That is the same in the Blackboard. I'm just here in the Blackboard. I'm just explaining all the details. All right. Okay. With that, let's try to.
Sorry. Could you comment on the bosonic case?
On the bosonic case, perfect. Yes.
Well, maybe not do the whole.
In the bosonic case, there are no nuclear spin degrees of freedom, but I can have collisions between this and this anyway. In the bosonic case, the Pauli statistic doesn't enter. The wave function is symmetric. So in principle, for bosons, I can have mostly S-wave interactions. The D-wave interactions are very high energetically costly, so we don't see them. For the case of strontium-88, for example, I have 3 scattering lengths: AGG, AEE, and AEG. 3. I don't have nuclear spin, so I can collide with these 3 parameters. Actually, strontium-88, for example, has this scattering length, AGG, almost 0. It's a coincidence, but that's why sometimes the people like it for clocks. There is very small the scattering length for this. This is 0, and actually On the contrary, for example, strontium-84, this parameter is approximately 200 atomic Bohr. So this is the people who do Bose-Einstein condensate of strontium-84. They use strontium-84 because they can do evaporative cooling. And the group of Florian Freck, now in Amsterdam, and the group of Kyoto by Yoshiro Takahashi, for example, they are using strontium-84 for preparing a Bose-Einstein condensate of atoms. Yeah? Okay. So let's now try to do an exercise and try to see how we are going to characterize these collisions with these Suos parameters. Yes? So let me start with a very simple case. That is what Jun wants to do in his clock. He wanted to do, I remember, take advantage that in principle there is only P-wave collisions that he thought he was going to be suppressed. So he is going to start with the case when I have just nuclear spin polarized atoms. I'm going to have what he uses is he has all these nuclear spin levels, but he's only going to populate this part. For example, the -9½ levels, nuclear spin polarized. And here, my only degree of freedom is the ground and the excited state. So G and E. So we go back to this case because I'm talking about this, in this case this, so I could have BEE, BGG, BEG, and UEG. These are the possible collision channels that I have. Okay, so let's try to write it and try to understand how they are. All right, so here in the slide, I already write the possible wave functions to simplify the dynamics. So we have now the G are here. This is the convention. G is blue, E is red. So there are three possibilities. I can have 3 orbital triplet states and 1 orbital singlet state. And then imagine, for simplicity, that I have 2 atoms, and one of the atoms is in one harmonic oscillator mode N1, and the other is in harmonic oscillator mode N2. I have these particles that are occupied these harmonic oscillators, and this is going to be, later I'm going to show you, this is going to be a good basis for the clock, for understanding the collisions. So let's assume that we are there. Two atoms they stuck into harmonic oscillator levels. And let's try to write the matrix that characterize the dynamics. Okay, so in this basis, then if I look at the collisions, this is in the T minus, T plus, T0, and the singlet. If I can have BGG collisions for the ground, BE, BEG, and the UEG minus interactions. This is the only S-wave interaction. Now, imagine I'm going to try to think about Ramsey spectroscopy, what we discussed last time. And remember that in Ramsey spectroscopy, in addition to the interactions, of course, the interactions are mainly important during dark time. I have to remember that the Hamiltonian, the single Campbell Hamiltonian, was something that is proportional to delta SC, and I have omega Sx. Remember when we were trying to do that, this is during the pulse, and this was during the dark time that is going to accumulate a phase. So I'm going to write the matrix in general here. So now, but this is a many-body basis. So remember that the operator Sx is a vector operator. So it's only coupled one of the G atoms. If I have GG, when I apply Sx, then this is the sum of x1 plus x2, and then it's going to couple to the triplet state. Yes, it's not going to. I need 2 applications in order to couple to 2 excited state. So the matrix element between the ground and there is a factor here, there is a factor here, and well, the different terms. And here I have delta minus delta and 0. Yes, because of the SC term in the single particle Hamiltonian. Yes, so this the SC is -1, +1, and 0, and also for the singlet I have this. So question, I'm reading here that this Hamiltonian is only coupling to the triplets. Why? Is there any possibility where I can also couple to the singlet? If I have a laser and I have two atoms, I have a laser, I have two atoms, so here I write I wrote maybe, let's put this over Sx. Can I couple, and because you can see that another way to see it is that this Sx operator is the collective Sx. It commutes with S squared, yes? Sx times S squared is equal to 0. So if I have Gg that has S equal to 1, or T, capital T, it's a triplet in this orbital degrees of freedom, then because this commute, I can only couple to the triplet, yes? Because this operator commutes. When I don't couple to the triplet, is when I don't have a collective operator, but instead I have omega 1 sigma x1 plus omega 2 sigma x2. If the matrix elements between, if the Ravi frequency experienced by the atom 1 and atom 2 is different, then in this case, I am able to couple to the triplet because, to the singlet, because this, now if omega 1 is different from omega 2, I don't have to preserve total x. You can also see it, for example, if I apply, for example, I start Gg, and then if G evolves as a different, I apply my pulse, and I have cos theta G plus sine theta E for the first atom. But then if the Ravi frequency is different, so I have cos theta prime for the G and sine theta prime for the E, you can show by multiplying these matrices that you are not remaining only in the symmetric manifold, but you have a component that goes to the singlet. Yes? So why the two atoms can have different Ravi frequency? Well, in principle they can, because remember the laser, and this is one of the points that we discussed also a little bit last time, the laser is e to the a kx. This is, let me pull this bare Ravi frequency, yes? And in principle, atom 1 is in harmonic oscillator N1, and atom 2 is in harmonic oscillator N2. So these matrix elements, they don't have to be identical, yes? They are only identical if k is equal to 0. If k is equal to 0, of course, these wave functions are orthogonal, and therefore I have the same Ravi frequency proportional to omega 0. But because they are in different harmonic oscillator modes, actually this is not the case, and actually you can show that this matrix element is proportional to a Laguerre polynomial proportional to n times eta squared, where eta is some decay parameter that is k harmonic oscillator length. Remember, the harmonic oscillator length is the square root of h in omega. So so in principle, this matrix can be slightly different, yes, if they are different two modes. But the difference can be very tiny if eta goes to 0, because the Laguerre polynomial of 0 is 0. So, but in the case where they are the same, imagine that they are the same, I'm only going to stick in the triplet manifold. Okay, so if they're not 0, then I couple to the singlet. And in this case, I can go from here to here. Notice that this is at the beginning, when Jung was started to see these collisions in the clock that were important. We thought that was the reason. We thought that the Ravi frequency was very inhomogeneous. It was trying to couple triplet to singlet. And even if you only consider, if you neglect the P wave interactions, we only consider S wave that are dominant, then because if you were coupling into singlet, you can start to have an issue with density shifts because you start to probe this extra frequency. It happens, as I will show later, that actually this omega bar, this delta omega is very tiny, and this is not the case. So the most important contribution from what they see from the collisions are actually determined by these BEG matrices. Mm-hmm. This is this is one of the first intuition of what happened. Now I'm going to ask you to rewrite. We are going to rewrite these matrices in terms of Pauli operators or spin operators. So okay, yes. So initially we thought that this was the density shift, but it was ruled out later. So now. This will look a little bit messy, but it's going to be the way that we are going to characterize the collisions in the clock. And for that, let's start. I mean, ignore the sum here. Put j and j prime just equal to 1 and 2. Mm-hmm. And what I want you to show you is that this matrix that we were writing in the blackboard before, BGG, BEE, BG plus, UEG minus. At the moment, let's only consider the collisions. This is the triplet minus, the triplet 0, the triplet plus, the triplet 0, and the singlet state. This matrix can be written as this part in the blackboard, on the top. Let's start, for example, giving an example. For example, I'm going to show you that this Hamiltonian here give me BGG. Mm-hmm. BGG. And then I would let you do for yourself, this is your homework today, try to reproduce and show that this matrix also give me all the other coupling, all the other interactions that I have here. Yes. So, for example, let's start. If I have an state that is GG, then I know that S dot S acting on these two atoms is 1/4. I know that SC is also 1/4, and I know that SC1 plus SC2 is here. This give me is minus 1. Yes, because I have 1/2 minus 1/2 minus 1/2 is minus 1. Yes. So the point is that if you look at this component, so I'm going to have what I call J perp, that is the part that goes in front of S dot S. This term is the difference between these two, BEG and UEG. Chi is actually the interaction between BE, BGG, and minus 2 BEG. C is BE minus BGG, and then I have this matrix that is just the identity, that is the sum over all interactions. Mm-hmm. So you can see that, for example, if I look at, because I have the same value for these two terms, mm-hmm, and then I have this value for this, you can see that this term, for example, cancels this term. Mm-hmm. And then because I'm also summing this and this, then these two are going to cancel this term. Mm-hmm. When I'm summing up there. And also, for example, then when I have this SC term, then because I have, in one case, I have minus term, so when I have this minus here, I'm going to compensate this with this, and I'm going to, in this case, these are going to cancel, the BE is going to cancel, this is going to acquire a minus sign, so I sum these two, and that's what, I will not do the algebra, you can do it yourself, but you can convince yourself that writing this matrix, this very simple matrix that is diagonal in these interactions, can be written in this form. And why I'm going to use this very complicated, you might be asking why instead of using this diagonal form I use this, because this is going to be the key to trying to understand the density shifts or the different ticking rates that they measure when the atoms, when they were interrogating the clock with Ramsey spectroscopy. Any question here? Okay, okay. So let me go. This is for two atoms. Now, what I want to, what is happening? Okay. Now I'm going to go for many atoms, and for that, and this equation looks a little bit complicated, but it's the way that we are going to describe the many body collisions in the clock. So, if you look at we are going to now go to second quantization. And in the second quantization, I'm going to define the creation and annihilation field operators that create a particle at position r. Who has seen field operators before? Okay, great. So, because we are dealing with fermions, now I'm going to talk about here nuclear spin polarized states at the moment. So I'm going to have m equal to 9/2. So the only two operators only the alpha here, the alpha and the beta, are going to refer to 9/2 and to the ground and the excited state. So because we are talking about fermions, these operators satisfy the usual anticommutator relation properties for the fermion operators, yes? They anticommute. Okay, so now let's start to look at what is the different contributions for the Hamiltonian. The first contribution has the single particle energy. This is p squared over 2m, and the external potential, that is in this case is the lattice potential. This is the first term. Now, maybe you are used to the case when you are having S-wave interactions between two different internal levels. These interactions are going to be the number of atoms in E times the number of atoms in G. Yes, this is the typical S-wave interaction that you write for S-wave interactions, and this is proportional to the scattering length, Eg minus. Remember, for nuclear spin polarized, this is the only one interaction that I can have, the Eg minus term. Now, for the P wave, remember that I introduced yesterday the pseudo potential for P wave that have k dot k prime. Oh, by the way, Juliet, I sent you the notes for the P wave. Okay, perfect. So you will have the derivation of the pseudo potential that was in momentum space. Now, for the case when you go to position space, remember k of the k operator is replaced by a derivative. So the pseudo potential for P wave interactions is proportional. Well, first we have the collisions that can be GG, EE, or EG. That's the three possibilities. And then I have P wave interactions. Remember, you have KK prime. So dot product for the pseudo potential. So let me write it again. The pseudo potential for P wave interactions P K prime was proportional to the B volume square K dot K prime with some proportionality constant. Yes? So the way that we write the P wave interactions is going to be with a gradient here that is replacing the P wave, the K, and then I'm going to have a dot product that is these dot products, the other term. So this is the fact that I have here. So you can see that these terms are kind of inverted. I mean, I have the gradient here first, and the second, the gradient is here. This expression guarantees that the only interaction happens between antisymmetric wave functions, because we know that P wave is only for antisymmetric wave functions. So in this case, it's just we just guarantee that we have the standard because remember fermionic operators anticommute. So when I flip this, for example, I get a plus sign here. And therefore they are not canceling out, but they are adding it together. So this is the S wave, this is the P wave, and sometimes, for example, I have a drive that promotes particles from the ground to the excited. This is the S plus term or sigma plus term, and then I have the characteristic K vector of the laser, and I have the laser wave vector that we can always go to the rotating wave approximation and change omega 0 by omega 0 minus omega laser, that is the detuning. All right, so this Hamiltonian looks awful, yes? I mean, if we want to really solve the dynamics of these particles, it's going to be impossible. So here is the trick. That's what we did for trying to try to understand the dynamics. The idea is the following. The idea is that the collisions are very weak. So remember, okay, what I'm going to do is that I'm going to consider the particles in a given harmonic oscillator. I mean, we have a lattice site, lattice potential, and each of the lattice potential, for each lattice potential, this is along the z direction, but along the xy direction, I have a two-dimensional harmonic oscillator. So the particles are trapped in an harmonic potential. So what I'm going to do is that I can always expand my field operator in terms of harmonic oscillator terms. So if I'm going to expand my field operator here of particle alpha, remember the lattice is very deep, so I only occupy the ground level in the z direction of the lattice. Yes? So along the z direction, I only occupy the lowest harmonic oscillator state, n equal to 0. But in the clock, they have a system that has microkelvin temperature, and then these trapping frequencies of the order of 500 kilohertz or hundreds of kilohertz. So under this picture, because the mean atom number is going to be proportional to chi Bosman T divided by h bar omega, if you look at for typical frequency of hundreds of hertz for trapping frequencies, for temperature of the order of 1 microkelvin, then this quantum number can be as of the order of 100. So it is very large. So I have a thermal number of states occupied in the different harmonic level. So I'm going to expand my field operator as creation operator of, or destruction operator, because this is a field operator of particle alpha in mode n, and the mode n has components nx and xy. And these phi sub nx, phi sub ny are just the standard harmonic oscillator wave function that you know in terms of Hermite polynomials. All right, so now the interaction term. The interaction term, all the terms that I wrote in the last slide had four different creation and annihilation operators, two creation and two annihilation operators. Yes. So when I plug this function into this, then I'm going to have four different operators, in principle with different quantum numbers, n prime, n2 prime, and nt prime. It's a complicated expansion, but and these coefficients are going to determine if I use for the S wave term or for the P wave term. In the P wave term, to go back to this, for the P wave term, I have gradient here, and I have a gradient here, dot another gradient here. It's a divergency. So you can see that if I have, then I try to expand these terms, then the contribution, this I have something that is proportional to the scattering volume cube, the scattering volume B cube. And then by units, because this is cube, this has to have units of energy, and you can show that this is divided by the harmonic oscillator length along the radial direction. And then the term that is proportional to here is proportional to omega c to omega r. So in that case, so let me explain a little bit here. The point is that I'm going to have, I have something that is the gradient alpha beta minus alpha gradient beta, something like this. This is the first term, for example. Dot the complex conjugate. You can see that when if I write, for example, if I have along the z direction, for example, I have derivative respect to z of phi 0, and then I have phi 0. This is along the z direction. Then I'm going to have phi 0 minus derivative of z at phi 0. This cancels. So there is no component along the z direction because they have the same wave function. This is again saying the p wave interactions needs an antisymmetric wave function in order to be non-zero. So the only non-zero components of the p wave that have the gradient only happens between terms that have the y or the x components, but they don't have the z components. Yes. So these matrix elements are going to have. The wave function is going to be, as I said, the wave function is going to be a component along z, a component with mode n along x, and a component with mode m, or we call it nx and y along y. So when I plug this into this formula, you can see that when the gradient is acting, for example, along the x direction, there is no gradient along the other directions. So that's why I have something that has an integral over 4 different functions. But for the p wave part, I have gradients. I have the derivative here and the derivative here. So this is a lot of details. I don't want to enter in, in a lot of algebra. I just want to show you that the s and the p integrals have a gradient or a derivative. The this integral that are also part of the p orbital matrix element. The p matrix element have a component that is s wave, p wave, s wave. That's the integrals that enter in the Hamiltonian. Okay, the important part now. You are seeing that everything is very messy in this formula. So what I'm going to try to come up is with the simplest model of collisions that we can generate. And the simple model of collisions use the following properties. Along the radial direction, I have many modes populated, many modes. But the p wave, remember the p wave interactions have the centrifugal barrier. And the centrifugal barrier can be as large as 30 microkelvin. Whereas the interactions, the temperature of the particles is just only 1 microkelvin. So p wave interactions tend to be suppressed. That means if I have these particles populating here, if they collide, the interactions don't have enough energy to redistribute the particles because changing the harmonic oscillator mode can cause up to 500 hertz of energy. And the collisions that we will have are going to be of the order of hertz or less. So the only choice that the interactions can do is to keep the atoms, the particles frozen in their mode, but they can only flip the spin. So in this case, the kind of interactions that I can have is I imagine that I have these particles frozen in these harmonic oscillator modes, and the only thing that can happen is that the particles change the internal degree of freedom. So that's the key of how we are going to model the dynamics. Instead of the particles spin in a lattice or spin in position, what the particles is that the particles are going to be pinned in energy space. So this energy space are the single particle harmonic oscillator levels. These are going to be kind of the lattice for these particles. But now the interactions are going to involve these complicated integrals between Hermite polynomials. And the important part is that interactions can be in these bases, can all-to-all. So, for example, if you have particles that are contact interacting in position, in momentum basis, these particles, the interactions are completely all-to-all. So the Fourier transform of a delta function is an all-to-all interaction. So what I'm going to model this problem that is very complicated, imagine fermions colliding at microkelvin temperatures with each other, is a very messy problem. What I'm going to simplify it is because the particles are pinned in these harmonic oscillator levels. I'm going to simplify as particles pinned in an energy lattice, and the only thing that they can do is flip or is interchange the spin degree of freedom with coupling constants that are going to be determined by these nasty p wave integrals that I showed you before. So now the important part is that even for many particles, if I have, remember I have different I have C daga n, C daga n prime, CP, CQ. I have different labels for the interaction term. But the important part is that I'm forcing, because I don't have mode changing collisions, I'm going to force two of them be the same, because otherwise I'm going to change the mode. So I have, for example, in this case, this term equal to this, and this term equal to this. Or I can have the opposite, this term equal to this, and this term equal to this. Now, I can define, in terms of a particle creation annihilation operator, an effective spin operator, yes? So this spin operator, I'm sorry, maybe sometimes the notation is complicated, but let me explain a little bit. If I have something that is C dagger up and Cn down, this operator destroys a particle in down, in mode n, and move it to up. Yes? So this is an S plus operator. The opposite for S minus. And now, if I have the same index, C dagger up, C up, N, minus, down, down. This counts the number of particles in up minus the number of particles, or I can write it maybe. This is up, up, minus down, down. And this is an SC operator, yes? So from this complicated expression of when I have four operators, I'm going to have a sigma C interactions. And when I have this type of terms, I'm going to have a sigma plus, sigma minus, sigma plus. So this is, with this, then the very complicated Hamiltonian that I have with many different field operators reduces to just a very simple, okay, let me start by telling you, reduces to this Hamiltonian, and this Hamiltonian is exactly the Hamiltonian that we could derive for just two particles, yes? So that's the point. So I'm just going to show, the only difference for the two particles, I'm going to sum over different harmonic oscillator levels that the particles are occupied. So I have my atoms, I put them in different harmonic oscillator levels, and I'm going to sum over the different harmonic oscillator levels that are populating. So I can map the Hamiltonian of particles moving in this harmonic oscillator in a very complicated way to a much simpler problem of magnetism where I have a spin model, and I'm going to show you that we can analytically solve this model. Any question here? I know that this part is start to become a little bit messy and you have not been very familiar with big wave collisions. But I hope you are getting the idea, and if not, please ask. Any questions?
What is the I?
The I is the identity. Now, before I have a C, now because I have another particle, I'm going to put the identity there. So yeah, sorry, that's a good question. So I am operating onto two particles. So the first operator acts in particle 1, and the second operator in the second particle. And if there is just identity, it's the very trivial step. So I really, please tonight try to show that for two particles, this Hamiltonian gives me the very trivial diagonal matrix BEE, BGG, BEG, UEG minus. This is another way to write this Hamiltonian. The only difference that I have is that I'm summing this in terms from this over the different harmonic oscillator levels over pairs of particles in my system. Yes, that's the difference. Going from two body to many body is just I sum over the interact. I put my particles in. So what happens is that I have harmonic oscillator levels. Then I use a Boltzmann distribution to place the particle with some probability in some orbitals. And with this probability, the interactions are just the sum. This particle interacts with this particles interact with this particle interacting this. And these interactions are in terms of these coupling constants, J perp, chi, C, and this, well, the constant is not important. And these are going to be determined by the corresponding volumes, scattering volume and scattering length. So still, this looks a little bit messy. So there is a simplified aspect there that it's going to be important. So again,
May I?
Yes.
It's on the fact that everybody is why is it that you cannot like an atom going up and the other one going down? This is still conserving energy even if
Okay, the potential, even though you have an harmonic oscillator potential in principle, is a Gaussian potential.
it's slightly anomalous.
In general, it's only true for the lowest levels that you really are a harmonic oscillator for the. Yes, so energetically, and the point is that sometimes, even though these collisions might be happening, you can show that as long as the energy is the same, then treating them as an spin, it's not that important to distinguish particles that have almost the same mode because they behave very similar. So even if they were the case that they were mode-changing collisions, as long as they preserve energy, still the spin model could provide a very good description because they belong to the same energy shell. Yes. Now, one more approximation. If you start to compute, one way is to compute all these nice nasty integrals that, all these nasty integrals that I was showing here. Jesus. Well, one possibility is you compute all these nasty integrals that you have in the model, and we have done that. We compute all of them. But other ways trying to introduce some intuition and see how they behave. Yes, and I'm going to try to give you some intuition on how this very complicated matrix element behave. And for that, I'm going to go, to the wave. Remember that the kernel, the pseudo potential for P wave interactions has, and now I'm setting k equal to k prime to get intuition. They were proportional to the scattering volume and divided by the volume and proportional to k squared. Now to have the units right and to make everything here as an energy, well, you can see that this is dimensionless and this part has units of energy. Now we have our volume of the wave function, and the volume of the wave function has two components: the area along the x and y direction, and along the z direction, I always in my ground harmonic oscillator level. So there is an area for the xy part, and then I have the z component, the harmonic oscillator length along the z direction. Now, if you remember, if I have a thermal distribution of classical particles, if I have a thermal distribution of classical particles, I characterize by some temperature T. How you relate the width of your distribution or the variance of your distribution in terms of the temperature? A very simple formula is the variance of the distribution is associated, in this case, well, this has units of harmonic oscillator, units square. And the width is proportional to k Bosman T divided by h bar omega. Yes, this is the character when I have a thermal cloud, and I'm going to see what is the extent of my cloud for a cloud of thermal atoms. You can show that the width grows with temperature. Of course, as I make my particles hotter and hotter, they spread out and the density decreases. Yes, they occupy larger and larger volume as I go to hotter and hotter temperatures. So an estimate of this area is what I put here, is harmonic oscillator k Bosman T h bar omega. Yes, and also because equipartition, k squared is an energy scales with T. Yes, the kinetic energy is proportional to temperature. So you can see that T divided by T cancels, and these P wave interactions in a two-dimensional gas becomes completely temperature independent because it cancels. Even though we might say, oh, well, P wave interactions scale with temperature. Well, the fact because we have a 2D gas and also the density also decreases with temperature, then there is a perfect balance at 2D and this part cancels out. So that means that if I try to compute the average of this P wave interaction kernel, and I do all the integral numerically. This is what I'm trying to do here. This is as a function of temperature, and I'm going to try to compute what is the mean of these interaction matrix elements. You can see that the mean is completely temperature independent, and this very simple analysis predict. And I also can compute the spreading of this wave function, and the spreading can be 4 or 5 the variance of this interaction. So if I am plotting here an histogram of this distribution of this coupling constant, and I see that it's centered at some place that is independent of the temperature, and the width, interestingly, also is independent of temperature. It's independent of temperature and much more smaller than the mean. This is one first characteristic. Okay, this is the first part. The second is that, remember that I was telling you that depending on the harmonic oscillator level, the matrix element with the Ravi drive can change. And because the matrix, I have something that is n e to the akx n, and of course this was proportional to the legend polynomial n1. So it depends on n1. But when you start to compute numerically these quantities and the mean of these quantities, you can see that the mean is much smaller. I mean, for the temperatures that the clock is operating, here the mean is almost at this value is much smaller than the mean, that the deviation from the interactions. So that's what, to first order, we can consider that the Ravi frequency is almost constant. So this was this bar. Remember, I have for the two particles that I show you what the matrix element omega 1 and omega 2 were the same. We only coupled to the singlet space. Yes, we don't to the triplet space. We never couple to the singlet. Yes, so the idea is that because these matrix elements are almost uniform, and now from what you see from this analysis, the p-wave interactions are also almost uniform. They have some variance. It's not completely true that they're constant, independent of the mode, but they are relatively in temperature independent. To first very naive approximation, then what happens is that this complicated Hamiltonian is going to be reduced to a very simple spin model, where I replace the coupling constant chi by the mean, the coupling constant c by the mean. I have an n here because I'm summing over the identity in the other mode, and I have collective operators. These collective operators are the sum over all the atoms in my system. So if you go back, let's go back to this Hamiltonian. I also have an S dot S term, yes? But if I'm operating in the fully symmetric manifold, to first approximation, this is a constant, because I'm not populating the single state. It's like in the two-particle case, it's staying in the S equal to 1 manifold. So this operator, even though it's there, it's only a constant of motion. And the dynamics of my system is only determined by this very simple spin model. Very simple spin model. That I have a term that is the detuning. This is from the laser. Then I have a term that is proportional to SC squared with some term that is chi bar. And then I have a term that is C bar from this interaction time n times SC. Yes? So the advantage is that from all this complicated many-body Hamiltonian that I had, I was able to simplify the dynamics to a very simple Hamiltonian whose dynamics I can solve analytically. And that was key to understand the collisions in the clock. So for that, so I have only two important parameters, chi bar and C bar, that's it. And of course, depends on the number of particles. Now let's try to, and these are these parameters. C bar is the difference in BE minus BGG, and chi bar is BE plus BEG minus 2BEG. Now, let's try to do even a more simplified treatment, that is try to do a mean field approximation of this model. A mean field approximation of this model tells me my atom, one atom is interacting with the rest of the atoms, so I don't care exactly what the rest of the atoms does, so I can replace this operator as 2 times the expectation value of SC times SC. So that means that the other particles are acting as a magnetic field on my particle. So I have a SC squared term Hamiltonian. So I replace the SC squared Hamiltonian, I replace it by the mean times SC plus SC times the mean minus 2 times the mean square. This is a constant term. So this is twice expectation value of SC. That means that the particles are feeling an effective magnetic field that is proportional to the magnetization of the gas, expectation value of SC. So with this very trivial analysis, you can see that the density shift or the different detuning that the particles are, my apologies, the different detuning that the particles are seeing are going to depend on C bar times N, the number of particles, and are going to depend on the magnetization of the gas. And the point is that in the Ramsey spectroscopy, SC is only controlled by the first pulse area. Remember, I start with all particles along the Z direction, I apply a pulse, like what we saw in the first lecture, and SC is going to be actually determined by, SC in Ramsey spectroscopy, the expectation value of SC is proportional to minus n half cos theta, where theta is proportional to omega t. Yes, that's what we saw last class. So that means that my density shift is going to be proportional only to the pulse area, and it's going to be proportional to cos time cosine of this. And then this is another term that is just a constant. Now let's compare this very trivial formula with what they measure in the clock. So they change the excitation fraction by changing the pulse area. Here you can go from 0 pulse area, very close to the south pole, to maximum pulse area when the particles are all up. And I'm going to look at this shift, so this detuning, how much it's changing from the detuning, this delta, that remember was proportional. So this delta was proportional to n times C times 2 times SC. The SC is n half, but with the 2 is n, that is outside, and cos theta. So this is the very simple expression that I get. And then if I plot this expression, then I can reproduce the density shift seen by the clock very naively, very simple terms. So that was one of the very important developments for making the clock better. So if they had 10 to the minus 16 stability before, with this very simple model, they can operate at a point here where there is no density shift. So that means they operate by the Ramsey pulse. Okay, where it's here. They operate here at a point where there is no density shift. And with that, they could go from a clock that has 10 to the minus 16 stability to a clock that has 10 to the minus 18 stability by controlling the cooperating in this magic crossing point. So not only that, I mean, the fact that it's linear in excitation fraction, very linear, validated our very, I mean, you see that I started with something very complicated. I mean, you look at the blackboard and it was very messy integrals. I simplified it to something trivial. I mean, did a lot of approximations, but they work. So not only we were able to operate the clock at this spot first, but the second, by mapping the slope and the zero crossing to what the clock measured, we were able to determine the P-wave interaction parameters that we didn't know before. And actually, as I mentioned last class, computing by first principles these P-wave scattering volumes is impossible. For strontium 87, we cannot do it. I mean, it's really hard. But by measuring this, we were able to determine the value of this. From that, we were able, I mean, BGG was known because of photoassociation measurements. This we knew. But we didn't know BE or BEG. So there is the slope and the crossing point, and with these two, I was able to determine these two parameters for strontium. Mhm. And because they are independent of temperature, then it was very accurate. And I'm going to show you that, in fact, the determination of these interaction parameters was really accurate by these measurements. So I think I'm running out of time. So in the next, in my same lecture, so far I introduced a very simple mean field model that nevertheless is very classical. But if we are going to deal with many particles, something that we want to do is trying to go beyond mean field and see what is the effect of correlations in the system. And what happens is that the clock, we're able to measure these beyond mean field effects and try to involve what we call quantum fluctuations in the system and see. At that time, we could not see a spin squeezing. I'm going to explain a little bit what it is, but we were seeing a modification of the noise distribution because of quantum effects. Any questions? Mm-hmm.
So you said that the relations are temperature independent in 2D.
Mm-hmm.
So how do they scale in 1D and 3D?
Exactly. Okay. Perfect. Good question. So, so the interactions are n times p wave interactions are proportional to the density times the temperature. So in 2D, in 2D, I show you that the density is proportional to 1 over T because we have sigma in the denominator, we have sigma squared. In 1D, the interactions are going to be proportional. The density is going to scale like 1 over square root of T because it's only one dimension, yes? And in 3D, n is going to be proportional to 1 over T 3/2. That means that interactions in 1D, I mean, in this case, are constant in 2D interactions, are constants in 2D because T divided by T cancels. In 1D, actually, they grow with temperature as a square root of T. And in 3D, actually, they decrease at 1 over square root of T.
So does this tie in with density? If you look at the density of states of fermions, right?
It's related. It's related, exactly. Yes, it's related. It's a coincidence. I mean, this is because the P wave interactions grow with temperature. For example, the P wave, the S wave, this is P wave. If you look at S wave, the S wave interactions are going to scale only like the density. Yes. So the S wave interactions are going to be very important because as we go to lower and lower temperature, because you have the T in the denominator. Of course, this breaks down as you go to, I mean, at some point you have the Fermi energy, and the Fermi energy is what is going to determine most of the things. I mean, for bosons, the density cannot go to 0 to fermions. But yes, I mean, that's a good question. Other questions? Yes, so for you, try to do the homework that I said, that is trying to show that this diagonal matrix is exactly in the form of these spin operators. And with that, convince yourself that you get from all this complicated initial Hamiltonian something as simple as we got for the clock and to understand the collisions in the clock.